And there we go. Welcome everyone to our 7th webinar of Euro. So this webinar, sorry for the sound, this webinar is about OpenMP, and we have a series of webinars actually. And all these webinars will be given by Christian Terboven from RWTH Aachen University and Michael Klemm from OpenMP. Sorry. Christian, Michael, you can go ahead. Thank you.
Okay, thank you. And well, right now I would say good morning, but this obviously depends on when you will actually watch this recording. So my name is Christian Terboven from RWTH Aachen University in Germany, and I'm a member of the OpenMP Language Committee. And I'll be giving this tutorial or this webinar that starts with an introduction to OpenMP and then covers GPU programming with OpenMP together with
me. That is Michael Klemm. I have two roles. So my first role is I'm the Chief Executive Officer of the OpenMP Architecture Review Board. So I'm leading that whole standardizations body. And I'm also a long-term technical member of the language committee. I joined that in, I think, 2009. And my daytime job is I work for a company called Advanced Micro Devices, who you may know as a processor and GPU manufacturer. And there my job is to take care of all kind of software questions and make sure that software runs best on AMD's platforms.
Okay, thank you, Michael. So our plan is that I start talking. If you have questions, you might be using, or you might use the chat in Zoom, and Michael will be there to monitor the chat and answer questions. And later on, we will switch. So that means Michael will take over, talk, and I will answer questions in the chat. But if you have more detailed questions that can't be easily answered in the chat, feel free to ask them toward the end of this tutorial. So we will not be speaking for the whole 90-minute session. So what's on our agenda? Let me stop the video here to save a little bit of screen real estate. So this is our agenda, and as we already heard, this tutorial or webinar on OpenMP will consist of 5 webinars. This is webinar number 1, which we titled OpenMP Introduction. So you're in the welcome right now. And in a few seconds, I will start talking about the fundamental concepts in OpenMP, which are the OpenMP parallel region, the work sharing constructs, and scoping. That means a determination if variables or data in general is private or shared. And then Michael will take over and give you a short introduction into OpenMP tasking, which is a different way of expressing parallelism, and then summarize how to execute and run OpenMP programs. But before we come to an end, there's a homework assignment. So we have prepared a set of exercises that we would like you to try out. And you can work on these exercises with all the things that you will learn and hear during this tutorial. And then when it comes to the next webinar, which is roughly in a month from now, which will focus on tasking in much more detail, we will start that next webinar with a summary of how to solve these OpenMP homework assignment. It's not a lot of work, but we would recommend, if you're really interested in working with OpenMP, to try yourself out, because these codes have proven to be useful, not for real simulations, but to understand the rough edges of OpenMP. Webinar number 3 will then take a closer look at the hardware. So we will talk about NUMA, which is non-uniform memory architecture, SIMD, also known as vectorization. And then webinar number 4 and 5 deal with the details of offloading in OpenMP. That means the exploitation of GPUs, for example, or in general, any other accelerator or coprocessor by means of the target construct in OpenMP. Again, we first do an introduction and then discuss more advanced topics. Further details on those next webinars will be part of actually those next webinars. That means a further detailed agenda. Okay, let's jump right into the overview of OpenMP. So what is it? It's a standard. I would call it the de facto standard, because it's not an ISO standard, which is, well, really robust in terms of developments, but also really slow in terms of developments. Yeah, so that means OpenMP is a de facto standard, which is developed and progressed by all its member organizations, both from industry and academia or public research institutions. It came to life in 1997 with the release of version 1, just supporting Fortran, and then over the next few years has incorporated support for C and C++ as well. If you take a look at this first block of developments and then this next block of developments, there was a little bit of, let's say, a slow pace in the development until 2008, when OpenMP 3 has been released. And this included the support for task parallelism. As I said, we will come to that later on. Michael will give you a brief introduction. And then again, there was a kind of more quiet phase until 2013, when OpenMP 4 has been released, which introduced support for accelerators, which will be the topic of webinars number 4 and 5. And then OpenMP 5 from 2018 brought, again, many new features and refinements to existing features, and also significant extensions to program for modern hardware, but also support for tools. And now we are in a cadence where we have new OpenMP releases every 2 years or something like that. So it's a standard that is not only around for quite a while and pretty major in terms of both the standard itself, but also implementations, but it's also alive and under active development. Given that it's a little bit older, yeah, in terms of computer science, at least the lifespan of OpenMP is kind of significant. It supports many different aspects. And people who looked at OpenMP, let's say 10 years ago and now come back, might have a hard time seeing the old OpenMP and what it currently offers. So I like this picture that has been attributed or added to our tutorial material by Ruud van der Paas, because depending from where you look at OpenMP, it might look as if it provides a different feature set or if it targets different use cases. But I would always argue that one of the strengths of OpenMP is that it combines all those different aspects into a single standard. So I'm not making any money of OpenMP, teaching OpenMP or selling anything like that. My job that pays me is, to some extent, user support. And I like that all those different aspects are integrated into a single standard, so I can, and that gives me a guarantee that all the tools work well together. So I still have the traditional OpenMP from 1997 that allows me to parallelize a for loop or a do loop in Fortran, and this is what we will start with in a minute. I also have this tasking, which allows me to express asynchronous operations to some extent. It allows me to parallelize recursive algorithms, irregular algorithms, and so forth. It allows me to integrate both tasking and work sharing with vectorization, which is important for modern microprocessor architectures, regardless of the actual vendor. Yeah, if I would have to go to a vendor-specific extensions to express vectors, then I might run into compatibility issues because the rough edges are not well defined. In OpenMP, everything is defined. And I can take all this that I already know from many years of programming for current, or let's say the past generation of supercomputers, and bring it to the current and maybe next generation of supercomputers by supporting accelerators. So I'm not trying to do marketing here. I'm trying to say that having support for all those different features in OpenMP is actually one of the selling points of OpenMP for programmers and users. If you want to follow this tutorial, and work on it on your own later on, there are a few references that might be useful. So we have OpenMP syntax reference guides. I think the modern word for that is something like a cheat sheet, but it's not a single sheet anymore. It's, I think, 4 or 5 pages. So we have those available for version 5, and I believe by now they should also be available for version 5.1. And they provide a brief summary of all the OpenMP directives, constructs, environment variables, API routines, and so forth. They are not meant as an introduction, but if you just want to look up the details on any of those, for example, construct that you know about, these cheat sheets available on openmp.org are really, really useful. They are available as a PDF, and you can print them out if you like, and have them available on your desk. There are also books. So the first one is a printed copy. The one to the left here is a printed copy of the OpenMP specification. Michael, maybe you can confirm this is available for version 5.1 as well.
Yes, and I will post a link into the chat window.
Thank you very much. So the specification is not really meant for programmers. Yeah, it's more meant for designers because it defines the semantics and the behavior of OpenMP programs and their implementation. But if you really want to take a closer look at how the program should behave, yeah, in many cases, a printed copy is more productive than working with a PDF. There are two books that we would like to recommend, and be careful. On one, I'm a co-author, so take my words with caution here. There's Using OpenMP, the Next Step, which has been written with the intent to teach all the important aspects of OpenMP. Most of these aspects are actually covered in this webinar, so I would say this is a good companion. However, the book has been written for OpenMP version 4.5. So that means in particular, some of the accelerator features like interoperability with CUDA or other languages and so forth are not covered in the book because OpenMP 5 has been released after the book has been released. But I think it should cover everything that we are talking about here. And then there's the OpenMP Common Core, which follows a different approach. So it tries to focus on the most important fundamental concepts and teach about parallelism and not go into all the, let's say, to some extent, confusing details, which is probably really good for learning, but sometimes it make you, it will not answer your questions if you want to solve a specific problem with your program code at hand, because that might not be addressable by the fundamental features. And this is why we have those advanced features and support for new architectures and so forth in OpenMP. Having said that, let's now really start with the content of this webinar. And the first important concept of OpenMP is a parallel region. But before I talk about the construct behind it, I would like to take a look at the machine and the memory model of OpenMP. And this figure that you see on the slide here is actually pretty old. So I stole it from a documentation from Sun Microsystems from 1998, because it represents an UltraSPARC-based architecture that was, let me call it, popular at the time when OpenMP was released and standardized and available in the first compilers from companies like Sun, IBM, and so forth. So this was the machine architecture that was dominant in the HPC world and also the large server world when OpenMP was designed. So there we had a set of processors like 4, which was a nice server already. They were connected via some caches and a crossbar or different interconnect technologies to the shared memory. And although systems look significantly more different today, OpenMP still targets something like that. So it targets a single node. We're not talking about individual processors here. We might have 2 in the traditional HPC node, but we have many, many more cores within a processor. So we might have 2 processors with, let's say, 30 cores each with hyperthreading enabled. So we have 30 times 2 times 2 equals 120 threads available in a single system. But these threads still have a certain cache hierarchy to their disposal. And we will talk about those interactions a little bit later on. And they all have a connection to the shared memory. And that's a fundamental idea. So we have many processing elements, meaning, for example, host processor cores or accelerators, and they have access to a shared memory. And in consequence, OpenMP is a shared memory parallel programming model. In the course of this tutorial, you will learn that it addresses almost all aspects of programming for parallelism, acceleration, and so forth within a node, but this is where it stops. OpenMP is designed to stay within the node. Real architectures are more complex than what I'm showing on this picture here, but for the beginning, we don't have to worry about those complications. And this is a view of OpenMP's memory model. So I said we have a shared memory, And then those T's are intended to represent threads. That means the threads of the OpenMP program that are being executed on this system. So the general assumption is that in OpenMP, if you have the node for yourself, you start as many threads as you have cores. This is not necessarily required, but for many use cases, this is a good assumption. Unless you use, for example, a hybrid program where you have one MPI process per node or per NUMA node or something like that, then you might run half as many threads as you have cores and so forth. Again, we will discuss that in more detail later. Those threads can communicate with each other via the shared memory. And with communication, I mean they modify a certain shared state, like a variable, like a flag or something like that. And we have synchronization constructs in OpenMP to enable that. And we will learn more about those in this webinar. But threads also have a certain private memory. That means they have copies or cloned instances of variables that only these threads can see and modify. For example, if you parallelize a loop, each thread needs its own loop iteration counter, the loop index variable. Otherwise, they would completely confuse each other, to put it in those simple words. So that means threads have access to the shared memory, but they also have their own private memory. And with programming languages like C and C++, you could access other threads' private memory from a given thread, but this is not allowed by the OpenMP specification. And violating this rule would result in undefined behavior. So what I'm trying to say here is that if you want to synchronize things, threads, and so forth, we really urge you to make use of the OpenMP synchronization construct that you will learn in this and the next webinar instances, and not write any synchronization constructs on your own unless you really know what you're doing. But I believe OpenMP supports constructs, clauses, and so forth for almost all important use cases. So synchronization is done via the shared memory, but OpenMP implements a weak memory model. So that means when a thread performs a modification of its local data, like it says a equals a plus 1, this update is not immediately visible by other threads. So this is why I have this private memory here as well. So threads can have local variables, and only after synchronization constructs, those updates are being written back to the main shared memory. And we have more examples to illustrate that later on. With OpenMP version 4, accelerator support has been introduced. So that means that in addition to the shared main memory, we also have accelerator memory that is accessible by threads from the main memory. For example, they can transfer data. We talk about mapping data in OpenMP, more details later. And we also have processing units on the device that can also work with this accelerator memory. So the OpenMP memory model has been extended to support accelerators. And coming from the memory model to the execution model, which I'm trying to illustrate in this simple picture here. So OpenMP supports, I call it fork join parallelism. And that means we have a master thread, this is blue thread here, that basically starts when your program is starting. So this is what starts the execution of main in your C and C++ program, for example. And then an OpenMP program consists of a series of so-called parallel regions. A parallel region means that the OpenMP runtime creates a set of worker threads. And then we have the master, and I believe we now call it initial thread, sorry for that. So the parallel region consists then of the initial thread plus the worker threads to form a so-called team of threads. And this team of threads is then available within a parallel region to execute your code and also obviously the OpenMP code that's part of this parallel region. At the end of the parallel region, the master or the initial thread continues. So that means you can think as if your program would run sequentially. What I'm trying to illustrate with these dotted lines here is that the worker threads are not necessarily destroyed, but instead they are being put to sleep. And that means at the next parallel region, they are more or less immediately available. And there's quite some logic and cleverness involved here. So putting threads to sleep, be it a light sleep, a deep sleep, and so forth, significantly reduces the overhead of the next parallel region. So the first one is more expensive than all the other parallel regions within your parallel program. And when you make use of OpenMP, you will profit from the many years that went into the implementations of the compilers and the runtime library systems and so forth, provided by your tool that provides OpenMP to you. So in OpenMP, you don't have to deal with thread management yourself. The OpenMP runtime takes care of more or less everything. And why did I replace master thread with initial thread? So technically, there's no difference. I didn't mean to confuse you, but this is a more politically correct expression. So initial thread is a term that we want to use from now on. And this is now the parallel region that enables the execution of multiple threads. So this is on the left box, you see the C++ code. On the right box, you see the Fortran code. I'm more a C++ programmer, so this is why I will tend to illustrate the examples using the C++ code here, but for Fortran, everything works exactly the same. So a parallel region has a well-defined begin. That means when this is encountered, this blue line here, the OpenMP runtime makes sure that inside the parallel region, which is a block denoted by these curly braces, the initial thread plus the worker threads execute the whole structured block. And as we will see later on, if there's a print like in Hello World, each thread will execute the structured block. There are a couple of requirements. So that means it's not allowed to use, for example, a goto or anything like that to jump from anywhere in your program right into the parallel region, or to jump from within a parallel region out of the parallel region. It's important to make sure that your program works correctly, to really follow the stream of execution that encounters a pragma OMP parallel and also leaves the parallel region correctly. Termination is allowed, so you can call abort and exit, and there's also cancellation, but we might come to that later on. But important is branching in or out is not allowed. But of course, within a parallel region, you can do whatever you like to do. That means you can call any functions of your program, any library routines, and so forth. You can notice that there's no number of threads. That means no degree of parallelism defined here. And this is usually done in OpenMP at the time the program is started. So we have an environment variable, which is named OMP num threads. And in most cases, you set this in your execution environment to a certain value to determine how many threads shall be used. And if you set it to 4, for example, the OpenMP runtime here will create 3 worker threads. And as I said, take the initial thread, so that within the parallel region, you have 4 threads in total, equaling the value that you provide to the OMP num threads environment variable. And there are also num threads as a clause that you can write behind the parallel. There are API routines to control the degree of parallelism and so forth. Okay, now let me show you how to execute an OpenMP program. And I think I have to change the screen sharing here. Give me just a second. Share screen. So Michael, it would be nice if you can just confirm that you can see my terminal here.
I can.
Thank you. So this is the OpenMP C++ Hello World. It's a very simple program. I have a pragma OMP parallel. And within this pragma OMP parallel, there's stdc out Hello World, stdc out IAM thread, OpenMP API routine of another OpenMP API routine. So I didn't introduce those on my slides yet, but OMP get thread num returns the ID of the calling thread, and OMP get thread nums returns the number of threads. OMP get num threads, not sure what I said, returns the number of threads present in the current parallel region. The ID is an integer variable value that starts with 0 up to n-1 if we have n threads, and then OMP get num threads returns n. So, and pragma OMP parallel is denotes the parallel region that I just explained. If I want to compile such a program, I have to tell my compiler to recognize OpenMP constructs. And for G++, I'm doing so with -f OpenMP. Michael has more details on that later on. And now, as I said, I can execute an OpenMP program and determine the degree of parallelism via this environment variable. OpenMP num threads equals 1 will execute my program sequentially. And here you can see that outside of a parallel region, or within the parallel region of only one thread, we have one thread in total, and this thread has the ID 0. Now, what happens if I execute this with 4 threads? Think about that for a moment while I take a sip of coffee. Is this what you expected? Not sure. And let me execute it again. You see, this looks different. So what am I trying to teach you here? So as soon as we think about parallelism, we have to stop thinking about any, let's say, implicit order in which things happen. So within a parallel region, as I said, each thread will execute the body of the parallel region, the body of this construct. And the order in which threads are being started, put onto the CPU and so forth, is not determined by the OpenMP runtime, but this is determined by the operating system, which knows nothing about your application. So that means things are to some extent non-deterministic. That means the order in which threads are being executed cannot be predicted. If you need things to happen in a certain order, you have to synchronize your code explicitly by means of synchronization constructs. And you also have to understand what happens if you use, if you call other code, like in this case, the std cout, which at the end of the day prints to a file, which here represents my command line window. You have to understand what happens if you call that from multiple threads simultaneously. So we see that those, let me use the editor again, that those, I would call it string tokens, these are not being mixed up. And we could talk about details a lot, but at the end of the day, there's some kind of locking, meaning synchronization within the standard libraries, so that any of these strings are being written as a whole to the file. This is not a guarantee of OpenMP, but this is a guarantee of thread safety provided by the implementation of the standard C and C++ libraries. But this, then this, and so forth is being executed by the threads, and they might be interrupted by the operating system at any point in time. So it means we don't know in which order things are being executed. So this is okay. In this particular code, each thread prints hello world, and each thread prints the I am thread so-and-so statement. But if you want things to be written in a certain order, you have to implement synchronization constructs, in particular for I/O. Good. I hope Michael answers all questions. If there's anything important, please interrupt me. Otherwise, I will now continue with my slides. Share screen. Okay. Now what we did so far was that all threads executed the whole parallel region. This is not necessarily meaningful because each thread performs the same work. So at the end of the day, we were just repeating or replicating work. With work sharing, the idea is that a certain amount of work is shared among the threads. And the most simple example for that is the parallelization or the parallel execution of a for loop in C and C++ or a do loop in Fortran. And in many cases, loops account for most of the program's runtime, and this is why the for work sharing construct was part of OpenMP from the very beginning, or meaning the do work sharing construct in Fortran, and then a little bit later on the for work sharing construct in C and C++. So the idea is that the loop iterations are being distributed among the team of threads, so that each thread works on a certain partition of the loop iterations. So in total, we achieve a speed up because multiple threads execute the loop simultaneously. And the scheduling of the distribution can be influenced, and I have a few explanations on the following slide. So what is this loop is doing? Well, this is a toy code, from 0 to 100. This is probably short enough to not being worse of parallelization, but I have an example later on. And I'm saying A equals B plus C, A, B, and C are vectors, and element-wise, B plus C are added, and the result is stored in A. How does that look like? Here, this is kind of a pseudocode, or it looks pretty much like Fortran, But in the sequential world, a version of the code, I would iterate from 0 to 99, and this is if this is now being split up to be executed by 4 threads. OpenMP num threads equal 4. What happens is as follows: there's thread 1 that iterates from 0 to 24. And it reads a certain partition of B, namely B from 0 to 24. It reads a certain partition of C and writes to a certain partition of A. The other thread performs the same code, but has a different iteration range from 25 to 49 and so forth. So in this case, the loop iteration space is distributed over the team of threads. What is important? Well, the threads all write to different locations of the array A, or the vector A, and read from different locations of the vectors B and C. And we will later on learn that this variable I has to be a private variable because this has to be present for each individual thread, because each thread has different values of I during the execution. At the end, let me just maybe I'm missing a slide here, but maybe I will come back to that later on. Okay, let me first add a few more details. At the end of each work sharing construct, there's a barrier. That means all the threads in the team wait there until all the other threads have reached the barrier. That means each individual thread of the team has to reach the barrier. And all work sharing constructs, and we learned about the 4 work sharing constructs so far, and there will be the a single work sharing construct in a second. So all work sharing constructs contain an implied barrier. Sometimes I call that invisible barrier at the end. So that means the construct only continues after all the threads have reached the completion or the end of the construct, because there's a barrier. If you need this to be explicit in your code, you can write pragma OpenMP barrier. So a barrier guarantees that all threads have completed the work before the barrier, but it does not guarantee that all threads start simultaneously after the barrier, because this again depends on the operating system. So a certain thread might be interrupted right after the barrier because the operating system has to do some memory management work or some I/O work and so forth. Then we have another work sharing construct, which is called the single, or which is named the single construct. Again, it consists of a structured block. Here I left out the curly braces. And that means that the enclosed structured block is executed by only one thread of the team, hence the name single. The runtime will pick a thread. In most cases, it will be the thread that arrives there first. And all the other threads will jump around because the content is executed by only one thread of the team. So if you want, for example, your debug variable to be printed to the command line and you don't want everything to be mixed up, you can make use of the OpenMP single within the parallel region so that only one thread executes the structured block within the single. However, that does not work if you want to monitor the difference between different threads, because you only get one thread. But in many cases, this is useful for I/O, for memory allocation or memory deallocation and so forth. And in some of the tasking constructs, parallel algorithms that we will see later on. And in OpenMP, we also have the master construct, but be careful, this is not a work sharing construct for whatever reason. So master means that the initial thread, the thread with the ID 0, will execute the structured block, but there's no implied barrier or invisible barrier at the end because it's not a work sharing construct. So if you need the master to do something and then all the threads to wait until this has been completed, you have to write pragma OMP barrier behind the structured block of the master. For the single construct, the barrier is implied. Okay, let me now show you the example of how to add vectors in parallel, and I believe then I will talk about the loop how to influence a loop distribution. I have to share the other screen again. Yeah, Michael, please complain if you can't see my terminal window. So I have a little bit.
I can see it.
Thank you very much. The code is a little bit longer here. So here we have 3 arrays A, B, and C, and they have a certain dimension. So this is large enough. That means the computation takes long enough to pay off the effort of going parallel. They are being initialized with 0, 1, and 2, respectively. And why this is important that we parallelize the initialization as well will be covered in the next webinar. Excuse me. What we have here now is a little bit or slightly more complicated OpenMP program that also illustrates some of the constructs that are introduced in the past few minutes. First, let me explain what we're seeing here. OMP get W time takes the current time. Here it's again taken, and if I subtract, the first value from this value, I get the execution of the parallel region, the execution time of the parallel region in seconds. Here we have a parallel region consisting of a single construct, so that means only one thread will execute this. It says computation started with so and so many threads. Here's this implied barrier, and then all threads will execute the for loop that parallelizes the iteration over this loop. So we always need the parallel region to have a team of threads, and in there the for work sharing construct. So this for construct binds to this parallel region. The parallel region gives us the parallelism, yeah, and then everything in the parallel region would be executed by all threads. And the for construct makes sure that the loop iterations of this for loop are distributed over the participating threads. So this is now the proof that OpenMP can actually speed up your execution. Again, I'm enabling OpenMP compilation here in the G++ compiler because I have some, let's say, cache intensive code here. I'm asking for at least optimization level 03. Now, if I execute this with one thread, it executes in 4.3 seconds. If I execute this with 2 threads, it executes in 0.22 seconds. Yeah? So it's an interactive system. It's not used for not usable for benchmarking. So I'm sharing this machine with 30 other users, but there's not a lot of things going on here. But we see that for 2 threads, we get a speed up of almost 2. It will not continue like that, yeah, because we have to take more care for such a code to respect the memory hierarchy, and we will cover that later on in more detailed aspects. Okay, let me go back to my slide deck. So what was done here by default is that the loop iteration space has been distributed over the threads in the team. And again, we are not writing our code with a certain number of threads in mind. Instead, we express parallelism, and the OpenMP runtime takes care of splitting up the iteration space. And that's really useful because we have the same code that can be executed with 1, 2, or 4 threads on the desktop, or with 100 threads on a highly parallel HPC node. We can influence how this distribution of loop iterations over the threads works. So by default, a so-called static schedule is being used. That means the iteration space is divided into blocks of a certain chunk size. By default, we have as many blocks as we have threads, and by default means there's no chunk specified. And then these blocks are assigned to the threads in a robin fashion. If we have as many blocks as threads, there's a clear mapping. Block 0 goes to thread 0, and so forth. If we specify a certain chunk size, Yeah, the blocks of chunk size means as many iterations are being grouped together to form a certain chunk, and then the chunks are distributed to the threads in the round-robin fashion. This is good for all codes that access variables so that the caches pay off unless the chunk size becomes too small. Yeah? But this is why static is a default. However, sometimes we have a load imbalance. That means iterations take longer, or some iterations take longer than others. This was not the case in my example, but I'm certain you can imagine some cases where this is true. If we then work with a static schedule, we always have to wait for the thread that has to perform in total the most work, meaning which got assigned in sum the most expensive loop iterations. If we want to change that, we can go to the, or to address that, we can go to the dynamic schedule. Here, the iteration space is divided into blocks of chunk, which is by default 1, yeah? Or you can specify a different value. And then these blocks are scheduled to the threads in the order in which they finish the previous blocks. That means whenever a thread has completed its chunk, it will take the next one. So again, there's uncertainty about the mapping of chunks to thread IDs, but it can address a load imbalance. And then for very special cases, but to be honest, I've seen very few in practice where this was better than dynamic, we have guided. So again, the loop iteration space is divided into blocks of a certain size, but the size is something you don't know. It's implementation defined. Sometimes your implementation tells you, sometimes they don't. And then these chunks are assigned to the threads. And over the course of the iteration, computation, the chunks are getting smaller and smaller. So they are decreased exponentially down to the chunk that is the size that is specified, meaning 1 by default. So it could be better because in some cases you have in total less chunks to distribute, which means a little bit less overhead in the OpenMP runtime. But in many cases, there's only little performance difference between dynamic and guided. Little meaning so little that it's hard to measure. The default on all implementations is schedule static. This is a slide I was looking for earlier. So this is the illustration here. So if we say schedule static, or if we say nothing at all, yeah, this is a loop iteration space. And this is intended to represent the cost of the individual loop iterations. And apparently my the explanation of the figure is gone. Maybe you can update the slide. Sorry for that. So you have to trust my word that this is what I want it to be. So this denotes the computational cost of the individual iterations. And by default, with a schedule static, the thread 0 would have to work much more than the thread 3, because here they get, or in both cases, they get the same number of iterations, but these iterations are computationally more costly. So they are relative, but so that means we have a load imbalance. We could go to a schedule static, 1, which is also what I explained. So that means we have 1 iteration per chunk, or 1 iteration to represent a chunk, and then we have a round-robin distribution. So this helps a little bit to address a load imbalance, but it often works not good on cache-based systems, which is what we have at the moment. Because if you access, for example, an array A at the position I, you always get more data loaded into your cache. So it would help to also access at position I+1, I+2, and so forth. So this is why a chunk size of 1 in many cases on a traditional CPU is not a good choice. So schedule static is a good idea for caches, but also it comes with a low runtime overhead. But we have this load imbalancing issue depending on your workload. Schedule dynamic can address that. I think I explained that. Yeah. But again, why it's not a default is that it comes with a higher runtime overhead to some extent. The chunk size has to be selected carefully. You have to respect the cache usage or the cache footprint of your code and so forth. And we will learn about later NUMA optimizations that become not necessarily impossible, but more tricky with a dynamic schedule. Good, I think I explained almost all on this slide early on. Okay, so after these details on the four work sharing construct, lean back a little bit. Now we learned we can express threads with a parallel construct, and we can parallelize loops with a for work sharing construct, or the do equivalent in Fortran. Are we now able to parallelize all the loops that we encounter in a program? Unluckily, the answer is no. Because sometimes there are dependencies in the code. And sometimes there are real dependencies, and sometimes they are just dependencies introduced by the way the code has been written. Let's take a look at this code example here. So we have a for loop from 0 to 100 again, and we are adding up all the elements of array A. What is the problem here? Well, if we execute this code in parallel, the iterations will be executed to some extent out of order. Is this a problem here? No, not necessarily. So that means we don't have any dependencies in between different iterations. But we have a problem with this variable s. So if there's only one s, at let's say a single point in time, two threads for different variables of values of I would read s, write their individual a of I to s, and write it back. If they execute that simultaneously, at the end of the day, one thread will go first, the other will go second, and the thread that will go second will override the partial contribution of the first thread. So we call that a data race. That means if without proper synchronization, there are two or more threads accessing the same memory location, and at least one thread writes to that memory location, then the result is not deterministic. We have a race condition because the result depends on the order of execution. And the data race then means this is causing a difference in the result of our data. And in most cases, this is an error in your program. And these are hard to find because on your laptop or so, where there's many other programs executing in the background, it might not be visible because your program is not really running in parallel. If you then put your program onto a server, then it will actually run into this data race because threads are actually able to execute in parallel. How can we address it? Well, we have synchronization constructs in OpenMP. One of these is the so-called critical construct. It implements a critical region. A critical region is executed by all threads. So that means if this is encountered in the parallel region, each thread will eventually execute the structured block, but by only one thread at the same time, because this implements mutual exclusion. So only one thread is allowed to enter the critical region, then able to execute the structured block. And only after this thread has exited or left the critical region, the next one is allowed to enter the critical region. And this is also true if you have multiple critical regions within your program and the same name. So the name is optional. That means if we have two critical regions with the same name, then only one thread is allowed to enter any of those, and only when that one thread has left, the next thread is allowed to enter. Having learned about this, we can address a problem that I explained earlier. So we can make sure that only one thread executes this update of the variable s, or the accumulation of array A. Do you think that solution scales well? Well, if you would execute it on a Windows machine and take a look at the task manager, you would see that all the threads are busy. But if you would measure the time, you would actually see that the more threads you take, the slower your program gets. That means it will take longer to be executed. Because what we're doing here is called serialization. Only one thread can be executed within the parallel program at each point in time. All the other threads will be busy, but waiting to enter the critical. Only one thread is able to execute the work that is intended to be parallelized. There are solutions for that in OpenMP, but first I would talk about the difference between private and shared variables. So far, we only learned that variables reside in the shared memory. So that means if you talk about an array A, there's only one instance of this array A, and this is referred to as a shared variable. All threads have access to the same variable. In order to avoid data races, it's important that in between synchronization points, threads only access different index positions of that shared variable A. But I think I made a note on that. We also learned about private variables so far. And this is the point here. The loop control variables on for or do work sharing constructs are private. I think I said that. This I variable has to be different for each thread because each thread performs a different partition, executes a different partition of the loop iteration space. And what I'm trying to list on this slide here are the default rules of OpenMP for scoping. And scoping refers to the differentiation of variables into private and shared. And by default, variables that are declared before a parallel region, meaning in the sequential part, are shared. And variables declared within the parallel region are private. And the technical reason for that is that variables within a parallel region are located on the stack of the threads, but you don't have to worry about that. You can just, in many cases, think about, does the initial thread encounter the declaration, or does the parallel the team's thread encounter the declaration? In the latter case, it's a private variable. A private variable is uninitialized. So it's a new instance of the variable. It has the same name, but it refers to a different thread for each thread in the team. If you want a private variable to be initialized, there's a first private clause, which makes a variable private, but copies over the value of the corresponding variable from before, for example, the parallel region. So it initializes the variable with the corresponding value from the initial thread. Otherwise, if you don't use first private variables, are uninitialized. And then there's also the loop control variable. So for or do work sharing construct, the corresponding variables are being made private by the compiler, but it doesn't matter. You are still allowed to say private I. That's still correct. And all variables that are not static and declared within a parallel region are also private. What is the special thing about static variables that are being shared? Well, you have to consider the lifetime of a static variable, static referring to C and C++, or a save variable in Fortran. So this exists even before the main routine starts. And if it's a C++ variable for C++ class type variable, the destructor will be called after main has been completed. And in order to carry over that lifetime concept to the parallel world, OpenMP introduced the so-called thread private construct. So if you have static or save variables and you want to make them private, that means to have one instance per thread, you will see you have to use pragma OMP thread private or OMP thread private in Fortran at each time this variable, or at each location this variable is being declared. And if you take a look then at your program in a debugger, in many cases it will be hard to recognize those variables because the OpenMP compiler and the runtime have to use different mechanisms to translate that to a correct implementation. But this is also, at the end of the day, what the C++ standard library does in order to guarantee thread safety. So the lifetime of a thread private variable begins when the corresponding thread is being created, and it ends when the corresponding thread is being destroyed. And if the runtime, for whatever reason, has to create more threads during the course of your program or has to destroy a thread during the execution of your program, more variables are being created, or again, they are being cleaned up. Why is it dangerous? Yeah. I would always recommend to avoid the use of thread private or static variables, because static variables are causing the issues. When you execute a parallel program and you change your parallelization, it's very easy to forget that a certain variable is static. It also makes a problem when you use other degrees of parallelism or use nested parallelism or composable parallelism, you always will run into special cases in which you have to deal with those static variables. I don't have the time to illustrate all those cases here. If you have questions, come back to us probably later or in another instance of this webinar. But what I'm trying to say is that there are some old books on Fortran and C that will teach you that static variables are faster. This is not true anymore. So if the only reason for a static variable is to make it faster because of that statement, please remove static or save. Sooner or later, this will cause you trouble when going parallel. The only really good reason I'm aware of for using a static variable is to write your own memory management routines like an allocator in C++. But if you're doing stuff like that, you also have to invest the effort to understand all the implications of thread private variables. Good. So back to our example. Now that we learn about static as shared and private variables, we have this parallel 4, and we have this critical in here. And I said performance is really, really bad. There's no scalability at all because of serialization. I wanted to write here, damn it. But my tablet was empty, so I'm using my desktop here. What we, at the end of the day, have to do is to transform this variable s. S has to be transformed from being a shared variable to a private variable. That means each thread, is working on its own. Where's my, whoops, sorry. Each thread has to work on its own variable s. Yeah, so my PDF display tool doesn't allow me to draw in here at the moment. Sorry for that. What I wanted to say is that this thread has to work on the S1, this thread has to work on S2, this on S3. Yeah? So that means we have to make S in OpenMP terms a private variable. We have to say pragma OMP4 private S. We have to be a little bit careful because in the original context, the variable S has to be used after the the parallel region as well. And I will upload a filled out slide into the PDF after this tutorial. Sorry for this technical problem here. But this is a standard use case. So the use case is that we have a certain variable that is used before and after the parallel region, and that's being read and written to, and that is a scalar variable. And for standard use cases, in many cases, there's also a standard solution, and this is called a reduction. So this is what the OpenMP runtime is doing for us when we say reduction plus :s. It will introduce a new variable s for each thread that only exists during the execution of the parallel region. And here at the very end of the parallel region, it will use a reduction operator to accumulate all the partial results. So each thread will work with this private s, and at the end, it will add the private contribution to the global, or meaning the original sum. Obviously, in the reduction, the initialization has to be done with a neutral element. So for the standard reduction operations, like plus, here we have the neutral element 0. For the multiplication, we have the neutral element 1, and so forth. We also have min and max. And with that, for the standard variables, meaning the built-in variables of the C, C++, and Fortran programming languages, we can use the standard operators as reduction operators. There are also user-defined reductions in OpenMP that we will discuss at a later point in time if you're interested. User-defined reduction means you are able to write your own operation that's being used to accumulate the partial results. For example, if you have strings, you can concatenate them. If you have irregular numbers, you can also work with them, and so forth. Good. Let me come to the final example of my part before Michael will take over. And I want to parallelize the computation of P. Well, P can be approximated by coming up with an approximate solution of this integral here. So from 0 to 1, we have to evaluate the term 4 divided by 1 plus x to the power of 2. We can do this by very simple numerical integration. Yeah, we have to evaluate the function. Yeah, this is a term here at many different, let me call them integration points. Not sure if this is the right English word. I'm always struggling with that. And this translates to code as shown on the left-hand side. Here we have the function f, that is a term 4 divided by 1 plus x to the power of 2. We have the loop from 0 to n, yeah, and n and the difference in between two integration points if one is 1 divided by n. We execute our function at this, yeah, we have to compute x, yeah, that is a difference between two function integration points, and execute the function here, add up all those partial results, multiplied with different to come up with an approximate of pi. And that's the idea. The larger the number of n is, the closer we get to actually to pi. Here I'm just saying pragma OMP parallel 4, and I would claim that this code is correct, is incorrect. Sorry, it will not approximate pi. So what is the problem here? Now this is about shared and private variables. In order to make the code correct, we have to say private fx and I. I is a loop index variable, so I explained that before. I doesn't have to be made private again explicitly, but it's okay to say so. Fx is a variable that's being written within each loop iteration, parallel loop iteration, and the value to fx is being dependent on the loop iteration variable. So that means for each time it's slightly different. It has been declared before the parallel region. That means it would be shared. So we have to say private fx to make sure that each thread here is working with its own fx. And fsum is very similar. It has been declared before the parallel region, but here we need a reduction variable. So we need the local fsum during the course of the computation because it's read and written in each iteration. And at the end, we need the accumulation of all partial results in order to be able to use that here. With that, I've completed my talk, and I just got a message from Michael on the side channel. No, sorry, I was confusing myself, but I would hand over to Michael. It's a little bit confusing that I don't see you here, Michael.
All right.
Are you ready?
Yes, you got to pass the beach ball to me.
Yes.
So that I can start sharing.
Okay, I'll take over the chat now.
Yes, please. There has been quite some traffic, which is really good. So thank you for that. I tried to answer most of the questions that came in, so feel free to ask more of them, and we'll have a Q&A session where, as Franz indicated, raise your hands and then either put it in the chat or unmute yourself and ask the question live. All right, I'm gonna close today, at least the slide content, with a very short introduction to OpenMP tasking. I will probably leave more questions open than I will answer, which I would call a nice cliffhanger for the next tutorial or webinar next month. And so what you've seen so far were rather regular patterns, right? You had like a parallel for loop or other very regular parallel constructs in your program that we parallelized with OpenMP directives here. And what I would like to talk about now is OpenMP tasking, which gives you a mechanism to tackle more complex and more irregular parallel patterns. All right, so slides advance. All right, so what is a task in OpenMP? So generally, what you can think about a task being is just a unit of work where you as the programmer tell OpenMP that OpenMP can execute that piece of work or that unit of work concurrently with other units of work. So what may happen is that this unit of work may actually end up in something like a task pool, and I'll come back to that later on the next slide. So either that work can be deferred in OpenMP language, so that means executed at a later point in time, or OpenMP may decide that everybody in the system is already quite loaded, so that work can be executed immediately. So basically, you just specify that you don't care when exactly it is executed and that it may be executed concurrently, and OpenMP will take care of actually executing that unit of work. So technically, a task is the piece of code that you want to execute. Like in Christian's example, potentially one integration point in the Pi example, or something to print on the screen, just the code that you actually want to be executed as part of that unit of work. And then, since that unit of work may be executed later in time, it also needs to carry everything that we need to execute that unit of work. So that means the task also has a data environment associated with it, so that the code has its data environment available when OpenMP attempts executing that task. And then, as kind of a speciality of OpenMP, there's also internal control variables, which are kind of part of the data environment, which control more information about how OpenMP should behave. But when you generally think about task parallel execution, code plus data environment, that's what makes up a task. And if you are a computer scientist, you may have the word closure ringing in the back of your head, which basically is the same concept of having code bound to a data environment for execution. All right, and then there are a couple of points where OpenMP tasks are being created. So the first one, again, is this kind of a OpenMP technicality, but you'll see the term quite frequently. So when OpenMP reaches a parallel region, as Christian has explained, at the fork point, when all the multiple threads, the worker threads, are created by the initial thread, these additional threads and their execution of the parallel region are called an implicit task. Okay, that's just take my word for now. It's all right. That's just OpenMP language lawyers talking. Then, of course, there needs to be a construct where you, as the programmer, indicate to OpenMP to actually create a task out of a certain code region, capture the data environment, and this is called an explicit task. And there's obviously an OpenMP construct for that called task to actually do that. Then there is the task loop construct, where you can take a parallel loop, and similar to what Christian was showing with work sharing, where the loop was cut into loop chunks, and then one chunk was assigned to a particular thread for execution, you can use the task loop construct to create loop chunks and assign each of those loop chunks to one OpenMP task and have the tasking model execute that loop in OpenMP task fashion. And then way later in the webinar series, we'll also talk about the target construct, which is also in OpenMP deemed to be a task creation construct or a task generating construct. So when you send something to a GPU for offloading and computation there, this is also considered an OpenMP task. And that gives some nice mechanisms that we'll explain in the GPU part of this tutorial. So when I said cliffhanger, there are a couple of those. All right, slides advance. Oops. All right, now the OpenMP tasking model. So as I already said, it's kind of made for unstructured or irregular parallelism. So you can parallelize things like this while loop up here, where you cannot really determine the loop space or the number of iterations or even how the whole loop behaves at runtime, you cannot determine that upfront, like with a for loop, where you know lower bound, upper bound, and loop stride. So you can basically do the math to assign the loop chunk to each of your threads. While loops are a different piece to tackle here. The other rather standard pattern is recursive functions. There will be actually an exercise on that in the hands-on that you can work on before the next webinar. But basically, anytime you have something like a sort algorithm that does divide and conquer, or recursive graph traversals, that sort of algorithm, you can use tasking to compose parallelism as you go on in the recursion and as you progress in that recursion and as you go down and create more recursive tasks out of this. And then, there's a whole bunch of different patterns, like single creator, where you have one thread or one task going through some sort of data, and anytime it iterates over one of those data elements, it creates a new task and produces work for consumers. That's actually something I'm showing on the right side of the screen, where we are still using master because the new constructs didn't really materialize in implementations yet, but where one of the main thread or the initial thread is working through a linked list, and for each list element, assuming computation on that list elements is heavy enough, it actually creates an OpenMP task and sends it off for some worker thread to work on that computation associated with that work item. You can, of course, have multiple creators. So these tasks here, while they're doing computation, they may encounter additional tasking constructs to even create more concurrent work and feed that into the workers, so that you get like many thousand or even millions of tasks throughout your computation, so that they can be assigned to your workers. And then, of course, you can obviously nest that. So as I already said, tasks and create other tasks. You can blend tasking with work sharing constructs to have multiple creators available. So your loop chunks in a work sharing construct can also create additional tasks. And as I already kind of mentioned a few times, all the threads in the teams are candidates to execute tasks. So anytime they run out of work and they're idling, they will look at the task pool and grab a task for execution out of it. All right, and then the kind of a standard idiom in OpenMP tasking, you saw that on the previous slide already with Parallel Master. In OpenMP 5.1 and going forward, this is going to be Parallel Mask. Christian already talked about the reasons here. So the idea is that you have one thread. While the main thread will encounter the parallel construct, it will create the team of threads to execute, and then you immediately restrict execution to just one thread. So either the initial thread, or you pick one arbitrary thread out of your thread team, and then this single thread then kicks off the parallelism, starting the task parallel execution. So that's kind of a very, very idiomatic way how you can think about tasking in OpenMP. And if you don't do any traditional work sharing like for or do, then this is actually the pattern how you would do it. In the main function, you would kick off OMP parallel, then do OMP mask or master, depending on your OpenMP version, and then have the remainder of your program inside that master region. You could think of this as similar to being in MPI, in the MPI world, MPI init and MPI finalize in an OpenMP task only program. All right, and here's the canonical example of computing Fibonacci numbers in a really interesting way. So the idea is, again, the main thread will kick off the computation. It will kick off the initial root of the recursion, and then going down through the recursion as long as n is larger than 2. Task to compute Fibonacci of n minus 1, store that into X. Then another task is to compute Fibonacci for n-2. And then we have to return x plus y. And so what we have to do also, and that's also very idiomatic, we have to, down here, we want to use x and y. So we have to do a task wait and make this task who kicked off that level of the recursion for n-1 and n-2. That one has to wait until the two child tasks for n-1 and n-2 are actually coming back, so that we know that down here, x and y are ready in terms of the result. If you wonder why there's a shared X and shared Y, I'll defer that to the next webinar. We will go through that, but you can basically assume that the idea here is that this X must be that X, and there are a couple of rules in OpenMP that would make the default be a private variable, actually a first private variable. We'll explain that next time. All right, and this is what happens. So thread 1, the initial thread, enters something like Fibonacci of 4. So it's doing that call and kicks off the recursion. And then T1 creates two child tasks for Fibonacci 3, n-1, Fibonacci 2, n-2. These two tasks will end up in the task queue or in the task pool. And then since T1 is now available in the task wait and is idling, it will grab one piece of work, T2, that's the other thread in our two-thread team, will grab the other task, and then both will create 4 new tasks. And so, you can basically going down through the recursion, you'll see that, you get multiple threads executing multiple tasks at the same time. And so this is how you can create parallelism in like a recursive fashion. All right. Okay, using OpenMP compilers, you already saw some examples of that in Christian's live demo on his system, but this is just giving you a little more extensive overview. So most production compilers actually have OpenMP support. I'm not listing all of them because there are probably too many. If you really are interested in, I already gave the link in the chat window, and you got the same link here on the slide. So the OpenMP ARB maintains a website where compiler vendors can tell us that they have an OpenMP compiler or an OpenMP tool. And then on a regular basis, like once a year, we will send a query to them asking for, hey, what's the current OpenMP that you're supporting? What product version do users need for that version? And that kind of update information. And so you can see, get a rough picture about the most important compilers on that website. Specifically, GCC obviously has an implementation, as Christian was showing. Then Clang and the LLVM compiler have an OpenMP implementation. And when I say Clang, I obviously also mean the Fortran Clang compiler Flang. Then the Intel classic compilers, so ICC or ICPC or iFort, as well as Intel's next-gen compilers, ICX, ICPX, and IFX. They all have OpenMP support. The AMD compilers, AOCC, AOMP, and ROCmCC, they also have OpenMP support. Actually, the next-gen compilers and the AMD compilers are based off of Clang and kind of work the same way as the Clang compiler. And then there's IBM XL, which is also supporting OpenMP compilation for IBM systems. And as I already said, there are many more implementations that I probably forgot to add here. Okay, the way you compile OpenMP, Christian had this already, is you have to tell the compiler to turn on OpenMP support. For most compilers, this is actually nowadays FOpenMP, so they kind of adopted what GCC was using. Intel has the speciality for their classic compiler that they also support -Q OpenMP. or in the next-gen compiler, they also support FI OpenMP. And there are subtle differences between using FOpenMP and FI OpenMP for the next-gen compiler. So you're best referred to the Intel manuals about what the differences are and which option you need to use. And then IBM has a slightly different syntax. They use -q SMP equals OMP to enable OpenMP support. And then the key thing to always remember is the switches have to be passed to both compiler and linker. So here I actually split the compilation of one of the hands-on exercise examples into a compilation step and a linker step, and at both you have to use FOpenMP or the respective version for your compiler to make sure that not only for the compiler OpenMP is turned on so that the compiler understands the directive, but also that the linker knows to pull in the OpenMP runtime libraries and everything it needs to actually link an OpenMP program. And then when you run it, here you see kind of a nice speed up for a naive implementation of a matrix multiply example. All right, and that brings me to the webinar exercises. So Christian and I put up a Git repository at this address, cterboven/OpenMP tutorial EUROfusion.git. If you want to work on the webinar hands-on exercises, please download the exercises using git clone. Then you can type in make to build the sequential versions of the hands-on exercises. And you'll find that a compiled code in a folder called bin. So you can run your examples always from that folder. The examples use GCC. There are some examples that actually require Intel's math kernel library. That's the Cholesky example. So you have to load the module or source the Intel environment depending on your machine so that math kernel library is actually being loaded and available through the environment. And then it should go through without any problems. And the idea is that we didn't say where you have to put stuff in the hands-on exercises. We just gave you a sequential code, and you have to figure out where to put the directive. Now, since we're nice guys, we actually put a folder for each example called solution, which shows the OpenMP directives that we have added to the code. So you can either use it upfront to cheat, or you can check if you came up with a similar solution as we did when we prepared the exercises. And as Christian has mentioned, we will allocate like 10 minutes or 15 minutes in the next webinar to quickly talk about the solution. So you're welcome back for the next webinar if you did the hands-on and you want to know what you did or what we did. All right, that's all I had to say. Let's open for Q&A.
Thank you, Michael. So I've been working in the chat. There's one discussion. Maybe you have an answer. Otherwise, I have to look it up. So this is about the lock hint clause that can be put onto a critical region. What is the name of the transactional lock?
OMP sync hint speculative with underscores between the syllables. So OMP underscore
speculative, right?
Yeah.
Speculative. I will just put it into the chat. So this is an pragma OMP critical. Is it just hint?
Sync hint.
Is it lock hint?
Sync hint.
No, the clause.
Oh, for the clause, it's hint. And then the hint for speculation is omp sync hint.
Sorry, there was a noise. Is it lock hint or just hint?
I'll type it into the chat.
Okay, and oops, I just put my guess here. You can correct that. So Samuel asked, will we cover hybrid OpenMP and MPI coding in a future webinar? So far, this is not on our agenda, I have to add, but we can add a few remarks. But there's not too much to it, I would say. Yeah. So if you understand OpenMP and you understand OpenMP, then we can talk about the implications of using both. So there's a little bit of what MPI supports, and then there's a little bit about progress. Yeah. But it would not justify a whole webinar, I would say. So
okay, there's a question, thread safety of MPI on should be addressed. Yeah, that's actually a good point. I mean, this is more a question for the MPI folks. We can certainly add a few slides here and there, and I'll make a note of that to show a couple of patterns how you can interact with MPI depending on what kind of thread level support you have in MPI. That's something we can certainly add to one of the advanced topics. I'll make a note of that. Thank you. There's another question. Will OpenMP usage or rather support on accelerated GPU be addressed? Yes, that is going to be part of our the last two webinars, essentially in, correct me if I'm wrong, April and May.
Right. So far, this is April and May, the last two webinars of the series.
Yeah, user-defined reduction will also be in a future webinar, likely the one on more advanced topics in 2 months.
Okay, so we're coming to the end of this session. I would like to remind all of you that this webinar has been recorded, including the discussion here, and the slides have been made available. So I think we have to make 1 or 2 updates. We will provide Franz with an update, and then all the material will soon be available. I think there's been a YouTube link posted into the chat already. So if you joined late, or if you or your colleagues are not available today, you will be able to watch this. And again, we invite you to work on the exercises and come back with questions for the next webinar. And as Michael said, and I believe I also said it, we have foreseen some part of the next webinar's time to answer those questions.
So thank you very much, Christian and Michael, for this very great webinar. I think we have a good attendance. So as Christian said, everything will be released on either EUROfusion website and EUROfusion YouTube channel. So I put the link of EUROfusion website in the chat, and I will put back again the EUROfusion YouTube channel in the chat. So just so you know, the next webinar is planned for Tuesday, 16 February, 9 a.m., 10:30 a.m. So this will be the continuation of this webinar. So thank you, everyone. Goodbye.